Power analysis is one of the most important yet often overlooked aspects of experimental design in the environmental sciences and engineering. In the northeastern US, oak trees tend to grow mixed in with maple trees. Are these trees in competition for water, or are they avoiding competition? It's really hard to just observe the root systems directly. They're below ground. You can't really do it without killing the tree. So what instead we do is look at the chemical composition of the water in soils and in trees. And we can come up with the hypothesis that the isotopic composition of oaks does not equal that of maples. We core 5 oak trees and 5 maple trees because coring trees is hard and it's cold out. Take the core samples, put them in a cryogenic vacuum extraction rig, immerse the samples in boiling water, extract the water into cold liquid nitrogen, thaw that water, put it into an isotopic analyzer and get some values. Then let's run the statistics.
Check out my awesome p-value. Everyone onto the dance floor.
Clark, did you check your sample size?
No, but it's fine, I'm sure. Oh yeah. Damn it.
What just happened? Explanation number 1, you're really bad at science, your hypothesis was stupid, you should quit and never come back. Possibility number 2 is just that your experimental design wasn't great. You probably didn't collect enough samples to actually test the hypothesis that you have.
We core 5 oak trees and 5 maple trees because coring trees is hard and it's cold out.
Let's just fit a normal distribution to these data for ease of looking at it. You can see that, yeah, like maybe the means are different, but there's an awful lot of spread in these values, and that's why we weren't able to test our hypothesis. So how do you know how many samples you need before you do the experiment? When I'm advising grad students on this type of problem, I see them take one of 3 paths. Path number 1 is I'm going to sample until I run out of time or money, and the experiment's going to stop there. Not a great idea. Path number 2 is I'm going to use the old standard n equals 30, and if it doesn't work, well, that was convention, it wasn't my fault. Path number 3 involves power analysis. The scientific method tells us that we have a hypothesis, we design an experiment, we collect data, and that's the end of it. We test our hypothesis. But that's not how science really works. We usually conduct a mini version of the experiment first, get preliminary data, and then use that preliminary data to guide the design of a much bigger experiment. Rather than throwing our hands up in the air, we're going to use this too small data set to do a power analysis so we can estimate the right sample size. The first thing we're going to do is set up another data set where we sample these observations with replacement. -6 shows up once, this -6.1 gets resampled 3 times, -6.3 shows up here, and interestingly, these two don't show up at all. So when we resample, we're very likely to get repeated measurements of one value and lose some other values. We repeat this resampling for both oaks and maples, and we calculate another p-value on this permuted data set, and we get 0.64. Let's just do this 3 more times. One of the times we got a p-value less than 0.1. That brings us to the idea of power, where power is the total number of resampled or bootstrapped datasets that gave us a significant result divided by the total number of bootstraps. We had 4 different resamples. 3 of them did not give us a significant result, 1 did. So we can estimate our power to be 25% for n equals 5. We can do a couple more things here. We don't have to just use 4 bootstraps to estimate the power. We can do this thousands of times. And we don't have to just estimate it for n equals 5. We can do n equals 10, n equals 30, n equals 60. And if we repeat this whole process over and over and over again, we can zero in on exactly what is the sample size that would give us the power that we want. Usually we shoot for a power of something like 80%. As we increase the sample size, we can see p-values dropping. Once we get out to a sample size of about 15, almost every permutation of this data set is giving us a significant result. Now let's look at power, which is the fraction of times that each permutation gave us that significant result. Sample size of 5 gave us a power of about 15%, which was close to our estimate with only 4 bootstraps, where we got 25%. So yeah, not too bad. If we wanted a power of 80%, we would go for 15 samples. If we wanted to be even more confident, say 95%, we would go with maybe 20, 21 samples. There's definitely not a strong justification to sample more than this. So going with that standard n equals 30 would likely just be wasting time and energy. So here power analysis is giving us a pretty decent idea of what we need to do when we go back out into the field the second time. We repeat the experiment, but this time sampling 18 oak and maple trees. Do the lab analysis, pull it into R, get a significant result. One last thought before I let you go. Scientific funding across the world is pretty limited right now, so the people giving out money for scientific experiments want to be sure that the work being done is low risk. Power analysis is sort of like the cheat code for getting funded and showing that your work is low risk. Yeah, it demonstrates that you know the sample size that you need, but it also demonstrates that you know how to go out into the field and collect the data. It shows you know how to do the lab analysis and you have the facilities on hand. It shows you know how to do the statistical analysis, the run through of the whole experiment. It basically demonstrates that you have probably encountered all the pitfalls that you're going to along the way. Therefore, your work is low risk. Have a good day.